Hello, and welcome to 3.2, Newton's first law of motion. In Chapter 3, we're going to be learning about three very important laws, all from a guy named Isaac Newton. You may have heard of him. He's the guy who apparently discovered gravity by sitting underneath a big apple tree. And an apple falls down, hits him on the head, and he says, "Eureka!" and understands gravity. Now, as far as I know, it's not actually a true story, but it's a good one to tell. So he's the guy we're dealing with, Isaac Newton. And he came up with three laws that changed the way we understood physics. It changed the way we understood motion. And it really created this idea of forces. So here we go. The first one is all about an idea called inertia. Inertia is the property of matter that resists changes in motion. Inertia is the thing that makes something not want to change how it's moving. And the most important thing here is that the more mass an object has, the more inertia it has. This idea of inertia was already understood. It already existed before Isaac Newton. But it wasn't really very formalized. Newton formalized the idea of inertia into his first law of motion, saying that if the net force on an object is 0, then the object will remain at rest or it will keep moving at a constant speed. At a constant speed. So basically what we're saying is if the net force is equal to 0, then that means that our acceleration must equal 0. It's saying it needs to stay moving at the same speed or stay at rest if there's no net force. And this is a very, very useful law that does hold in a lot of situations. Now, I like to restate it in a slightly easier way. I like to say just an object can't change velocity without a force. That's how I like to think about Newton's first law of motion. An object can't change velocity without a force. And notice I said velocity. That means it can't change speed or direction without some force. Okay, so who is this Isaac Newton guy? Well, he was born in 1642. And that's the same year that a famous physicist called Galileo died. And that's going to come up in a second. Isaac Newton, he published a book called the Principia Mathematica, and in it he published his three laws of motion. So I mentioned Galileo. He is the physicist before Newton. He died the same year that Newton was born, who really first formalized the idea of inertia, this idea that things keep on moving. So we're going to say down here how Galileo came up with this idea that things keep on moving at a constant speed forever unless there's some force on them. So Galileo's thought experiment, we've got this below. There's a picture of it below. The idea is that we take a ball. Take a look here. We've got our ball. And we let it roll down a ramp. And then it goes along a horizontal plane and back up another ramp. And what he found is when he did this, the ball would roll back up to the exact same height that it was before. So that the ball goes back up to the same height. And he noticed that this was true even if he changed the ramps. Look, the second ramp has a different slope than the first one, but still the ball ends up the same height. And so he said, okay, well, if I lowered this ramp even more, then that means it's going to travel even further before it stops. And he extended that. He said, okay, what if I make this ramp so it doesn't increase at all? What if the ramp just goes on forever? And that's this last scenario here. Well, if that's true, then the ball is going to keep on going until it's able to raise back up to the same height, which is forever. It's going to keep on going on forever. And that's inertia. Now, in the real world, this doesn't happen, and that's because there's a thing called friction. But the principle is sound. So Galileo's thought experiment, the idea is that a ball rolls back up to the same height that it started at always. And that can extend then to this forever scenario where it moves on forever. Great. So that's our idea of inertia. That's Newton's first law. He's formalized this. He's said that something is going to keep on moving on forever unless there's a force on it. And the funny thing is that's not what we experience in real life, right? We have something that's moving, it stops moving eventually. That's all because of friction, and friction makes this a bit more complicated. But when there's no forces, when there's no friction force, something will move on forever. And a good example of that is looking in space. If you've ever seen a picture of something going on in a space station, people just floating around. Okay. We're going to use Newton's first law to explain each of these situations below. First off, why does a computer sitting on a desk remain at rest? Okay, I'm going to draw a little system diagram of this situation here. Here's my little computer. That's my computer here. Doesn't look much like a computer. That's fine. There's my computer sitting on a desk. You know what? It's not a great system diagram, but the more important one is the free body diagram, where I'm going to draw the forces on it. There's going to be gravity. There's a normal force. Those are the only two forces acting on this. Use Newton's first law to explain this scenario. Well, the normal force cancels out gravity. So that means our net force is equal to 0. Therefore, it's going to remain at rest. Next one, why does a hockey puck moving across smooth ice move at constant velocity? So here's our little hockey puck, and it's moving along the ice. Here's some ice that it's moving through. If we draw a free body diagram of this, again, looking from the side for this one, again we have gravity going downwards. We have normal force going up. It moves at constant velocity, so there must be no other forces on it. Technically, there's a tiny, tiny bit of friction, but on ice, friction is so small that we can basically ignore it. And that's one of the reasons why we play hockey on ice, is because we can reduce the friction. So the idea here is that the friction is, well, almost 0. That means, again, that the net force is equal to 0. Finally, why does a wagon pulled across a rough surface by a child move at constant velocity? So we'll draw our wagon here. And here's our child pulling our wagon. Well, this wagon, if I draw its free body diagram here, it has gravity and it has normal force. It's got some tension or some applied force, and it's got friction. And what we're saying here is that if it's moving at constant velocity, then that means that F net has to be 0. That means, therefore, that our tension force has to equal to our friction force. They have to cancel each other out, because everything needs to add up to 0. So that's the only explanation why this, this cart would be moving at a constant speed. Again, this is a difficult concept, I think, to understand, that even though it's moving, the net force is 0. If it's not accelerating, the net force has to be 0. Okay, moving on to the next page here. Older cars did not have headrests, but all new cars do. How do headrests help prevent injuries during a rear-end collision? Use Newton's first law to explain your answer. Well, if I'm sitting in a car, let's look from the side here. Here's my seat. Here's me. I'm sitting in my car, just minding my own business. And this car doesn't have a headrest. Okay, I'm driving along. Actually, let's say that I'm not. Let's say I'm completely stopped, and then some car from behind smashes into the back here, applying a force. The whole car gets forced forwards. So the car gets forced forward, the chair gets forced forward, my body gets forced forward by the chair, but my head doesn't have anything to force it forward. So in fact, my head ends up going backwards relative to the rest of the car. Because my head's not moving at all. My head wants to stay exactly where it is, but everything else is moving around it. Everything else is moving forwards around my head. And then my head gets whacked backwards, and it's bad for me. So our explanation here is that the car moves forward, but the head does not. So the headrest helps move your head forward with the rest of your body. And you'll notice that when we're talking about Newton's first law, a lot of this is conceptual. We're talking about ideas here, and there hasn't actually been any math yet, or not much math. We do have a bit on this next problem, but Newton's first law is largely a conceptual idea, getting the idea that things won't move unless they have a force on them, or they won't change speeds unless they have a force on them. Okay, so speaking of math problems, here's a bit of math. This one says, what is the missing force on each free body diagram shown below? Figure A is an object at rest, and figure B is an object moving left at constant velocity. A is at rest. If it's at rest, that means that the net force equals 0. This is the start of what we're going to be doing for the rest of this chapter and the rest of this unit, talking about our net force in two ways. First, we can say that our net force is 0, and second, we can calculate our net force by adding up all the forces acting on our object. So here my net force is going to be 12 plus 8 upwards minus Fg downwards. I have two statements for F net. I can set them equal to each other. That means 0 equals 12 plus 8 minus Fg. And now we can solve for gravity. Fg equals 12 plus 8, 20 newtons. And there we go. Now the last thing is, we are talking about a vector. We should have a direction. That direction can be d for down. Letter B. Letter B is an object moving left at constant velocity. It's moving that way. So then the net force should be to the left? No. Our net force needs to be 0 as well, because it's moving at a constant velocity. So even though this is our velocity, our net force again needs to be 0 because the velocity is not changing. F net equals 0. Again, we can solve the rest of this here. If the total net force is 0, that means the x component of that has to be 0, and the y component has to be 0. So let's start with the x. F net x equals 0, and we can also figure out what that is equal to by adding all these x forces together. So here we have 28 to the right, minus 15 because it's to the left, and minus F1. Good. So then we have 0 is equal to this. We can rearrange and say F1 is equal to 28 minus 15. So that's equal to 13 newtons. And we can see that it's pointing to the left. So we can say that here. To the left or to the west. Let's call that west in this problem. Okay, and now we want to do F net y, our vertical components, and so we can add up these. We know that they need to add up to 0 as well. So our net force is equal to 0, and it's also equal to Fn upwards minus 22. That means that Fn is equal to 22 newtons up or north. I mean, we're not told what our directions are here, so we have a bit of freedom to say what we think they are. But here we have 13 newtons west, 22 newtons up. Perfect. Our last topic here, applications of Newton's laws. Newton's first law specifically, and we're just going to talk a bit about a seatbelt. Up above we talked about the headrest. A seatbelt, again, is helping us from injury based on Newton's first law. Here's how it works. In a collision, the pendulum well, I need to take a break now because I haven't actually explained this. So look at the picture down below. This is your seatbelt. This connects to the strap across your chest. Inside the hinge here, it has this gear with these spikes on it. And notice that this gear is free to turn. It can turn this way, it can turn that way, so it can tighten and it can loosen. But in this second picture over here, this green bit has popped upwards. And now, this can still turn that way, it can still increase, but it can't go back that way. And you probably know that feeling, that if you tug on a seatbelt very quickly, it gets locked, and it can still get tighter on you, but you can't actually force it to get looser again. And this is to hold you in place. The idea is that if we get into a collision, let's draw a little collision here. If we get into a collision, there's two cars here. And pow, they smack into each other. Well, if I was driving in this direction in my car, then my car all of a sudden stops. All of a sudden it gets a net force this way, whereas my body doesn't know that. My body still wants to keep traveling this way. I will fly out my windshield unless I have something stopping me. So my windshield, or sorry, my seatbelt is keeping me in place. It's keeping me from flying forwards. And again, the way that works is that this rotating mechanism locks, so that it can only get tighter, it can't get any looser, so it locks you in place. Okay, so now up above I'm describing how that mechanism works. So in a collision, this pendulum down here, this pendulum, it swings forward. It keeps moving forward because of inertia. Causing a metal piece to lock the gear in place. And that's how that works. So we've got a few different ways of protecting ourselves in our cars. Cars obviously need a lot of safety features. At the bottom, again, there's a set of questions, and I think you'll find that they are fairly quick to go through those questions because they're sort of conceptual questions. All right, have fun, enjoy those, and I'll see you in the next lesson.